the slider crank chain. Okay, this is also one of the mechanisms. Okay, this mechanism we call the planar mechanism. There is two kinds of the mechanism. I hope you know. There's a spatial mechanism and the planar mechanism. This slider crank chain comes under the planar mechanism. Okay, there are three objectives for this practical. Number one is to obtain the graph of piston velocity against the crank angle using the method of instantaneous center, assuming that crank rotates with constant angular velocity. So first of all, before I get into explaining the first objective, I give you a brief explanation about the slider. What is the slider crank chain? What it represents? This is the kinematic diagram, but it's actually, I think everyone is heard about the engines, right? There's an engine. So this is the piston, there's a connecting rod, then crank. So when the motor is, or when the crank shaft is connected to this this crank, so when it's rotated, this piston is moved in reciprocative motion. It's moved in a reciprocative motion. So this is the representation of that kinematic diagram for that mechanism. This is the one mechanism we used in the automobile. That's why we are interested in studying these slider crank chains. Okay. So today our first objective is, to obtain the graph of piston velocity against, this is the piston, so this is the piston. So we are going to get the graph, this piston velocity versus this crank angle. So this one is rotated like this. I must see, okay. So this one is rotated, let's say this one is rotated in omega, at omega angular velocity. So while this crank is rotating in this constant velocity, what's the velocity profile for this piston? So that is our first objective. Okay, keep in mind, because before, when you are doing practical, you have to always keep in mind what is your objective, why you are doing this practical. So your first objective is find out this velocity profile versus this crank angle, assuming this crank is rotating in at constant angular velocity. Okay, go into the second objective. Our second objective is to obtain the crank angles which corresponds to the maximum piston velocity. When it rotates at constant velocity, this velocity is going to vary. So our second objective is at what angle of the crank this velocity is the maximum. Clear? Okay. So second objective is find out what is the crank angle we can obtain the maximum piston velocity. That is our second objective. What is the third objective? Third objective is to show that for a slider crank chain, the piston motion tends to simple harmonic motion with increasing values of connecting rod and crank ratio. So first of all, I introduce the term, the connecting rod over crank. This is the ratio. So when this ratio is varied, what kind of this piston motion profile? So we are going to show with increasing this ratio, this motion profile is tend to be like a harmonic motions. That is our third objective. Clear? So keep these three objectives in mind while you are doing the rest of the practical. Okay, students, now we are going to I'm going to discuss I'm going to demonstrate some parts of this apparatus. Okay, this is our slider crank chain apparatus. So we are going to do the practical with this apparatus. Okay. So I'm going to explain or I'm going to tell what are the each parts of this slider crank chain. Okay. If you look at this one, you see I point here. So this one is called the base. Okay. This one is the base. So here you see number this one. It's called crank. This is the crank. Okay. After that, this is called connecting rod. This is called connecting rod. This is crank. This is connecting rod. Okay. This one is called, you see the below here. This one is the piston. Okay. This one piston, crank. So connecting rod and crank. So now you see when the crank is rotating at angular velocity, you see the piston is moving inland. Okay. So we are going to study these motions. Okay. Kinematic means we are interested in the motion of the linking parts. Okay. So we are going to study these motions. Okay. So here there is additional tools also they given to make us our practical too easy to read all the readings. So this is we call scale. Okay. We can read the how long this piston is moved. So by using this scale we can read how long the piston is moved. Okay, moving into the specimen calculation for our practical, we need to represent this cylinder crank chain into kinematic diagram. Okay, this is the O point. So here I denote as a O. Okay, and then it's a crank, it's a one link. So I denoted this one is a OA as represent the crank. And this one is representing the connecting rod. This, okay. Then this piston is moving in horizontal, right? So this velocity I denoted as a VB. Okay, VB. So this is the kinematic diagram representation of this mechanism. Okay. So we are going to come up with some useful equation, okay, in order to do this practical. Okay. So for these calculations, we are using instantaneous center method. Okay, instantaneous center method. By using instantaneous center methods, we are going to come up with some useful equations. Okay, let's start. Okay, if you take this connecting rod, okay. What is the instantaneous center at this moment, at given moment? You know, roll like this, and this one you connect. So this one, this I is the instantaneous center for this connecting rod. Okay. In the same way, I extend this one also in geometry. Okay, I extend this rod and perpendicular to this one I denoted as a X. Okay. I think basic physics you might know. When object is rotate about one given point, and this is the object, and this velocity is given by, you know, when the object is rotate at the omega velocity, angular velocity, the v is given by v equal r into omega. So this r is the distance, the perpendicular distance from the center, and omega is the angular velocity. So we are going to use this equation to find some equation. Okay, let's take this point. If you take this point, this VA equal R, here R is a OA, the crank length, OA into omega. Let's say it's rotate at omega velocity. In this practical, we are going to assume omega is unit 1. Okay? If we assume omega equal 1, then VA equal OA. Clear? Okay, we are assuming omega equal 1. Okay? Then consider this instantaneous center. So if you apply the same equation about this instantaneous center to this connecting rod, you see this point all going to rotate at the given at omega dash velocity. Okay, at a given time. Okay, so we can write down. So whatever you point take, this omega 1 is a constant at a given time. So omega 1 equal to VB into this distance. What is the distance? IB equal this VA equal IA. So VB is equal to VA over IA into IB. Clear? So using the instantaneous center method, I come up with this equation. Okay? Let's apply the geometric characteristic of these two triangles. Okay? If you are considering the characteristic of these two triangles, it's quite similar. So we can write this distance over this distance equal to this distance over this distance. Okay? So how we write? IB over OX equal IA over OA. Okay? So now what we are going to do is we are going to replace these things with these parameters. Let's say here you see IB over IA equal to, you see IB over IA equal to OX over OA. So now we are going to apply this one here. So VA, we can replace VA as a OA. Okay? Because we assume omega is 1. So OA into IB over IA, OX over OA. So this length and this length will be cancelled out. So VB equal to OX. Okay? So at a given point, at a given time, the VB is equal to the length of this distance. Understand? Remember, we assume omega equal to 1. Then you may be asking why VB is a unit, is a meter per second, OA is a distance. But we already assume omega is 1. That's why the VB is represented by OX. Clear? So now why I am interested in these parameters? Okay? Because you may wonder, when I showing all the parts of this apparatus, okay, this scale is used for measure this distance, the piston distance. But this scale, this is the center O, this is the center O. So this distance you can read from this scale, this cross scales. Understand? So that's why they given these cross scales. Understand? To do this particular practical. Understand? This is the theory behind this practical apparatus. Okay. Next, we are going to look at the we are going to do practical and getting the some values in order to draw a velocity, the piston velocity with the crank angle. Okay. Okay. Now we are moving into procedure of this practical. Okay. This is the scale I said on the specimen calculation. You know, this is the scale is used for read the OX distance. Okay, the OX length. Okay, so here you see the orange one is this is the crank. This is the crank. This is the connecting rod. Okay, this is the connecting rod. So the first step is what is we have to set the crank angle at 0. Okay, this is the 0. Okay, we set the crank angle at 0. Okay, then when the crank angle is 0, you see on a cross scale also 0 and on a displacement scale also 0. Okay, so we have to note down when the crank angle is 0. Okay, the piston displacement also 0 and the vertical, that means the piston vertical cross scale also 0, the OX also 0. Now what we have to do is we have to move the crank angle at 10 degrees Celsius. Sorry, 10 degree. So at 10 degree you can notice the piston displacement is 1 millimeter. Okay, if you read this scale, the piston displacement is 1 millimeter. Then on a cross scales, the OX length is, if you read carefully, is a 8 millimeter. Okay. Likewise, every 10 degree we have to take readings on these two scales. Okay, every 10 degree, like you see 10, then 20, we have to read this both scale, then 30, we have to read the both scale, and 40. Likewise, every 10 degree we have to take the reading until 360 degree. Okay, this is the procedure we have to do. Okay, by taking these two readings, we know what is the OX length and the piston displacement, because these values are we needed to plot the graph. Okay, to plot the graph to piston velocity versus the crank angle. Clear? Okay, let's move on to our tabulation part. Okay. Okay, now we are moving to the section of the observations. Okay, we already did the practical using that apparatus, and we take all the reading. So while you are taking the reading, you have to fill up this table. Okay, this is the crank angle, and this is the piston displacement. This is the cross scale reading, the OX reading. OX is equal to what? In specimen calculation, we also come up with the OX equal to the piston velocity, right? This is the parameter we are interested in. This is the parameter and this is the parameter we are interested in. Why? We have to draw the graph between these two parameters. That is one of the objective. Okay. So now we just fill up this one every 10 degree. You see 0, 10, 20, 30 until 360 degree. Then through the displacement scale, we read 0. When the 0 angle, the displacement, the piston displacement also 0, and piston velocity, that means the cross scale reading also 0. But when the crank angle at 10 degrees Celsius, what is the piston velocity? Piston displacement, we get 1 millimeter, right? Okay, 1 millimeter. What is the cross scale reading? Minus 7 millimeter. Okay, so likewise you have to fill up all the reading. Okay, now we are going to move into the results, the section of results. Okay, what you are going to do with the observation values? We already tabulate all the readings, the piston velocity and the piston displacements. Okay, so remember that what is our objective? Our objective is why we are doing these things so far. Our objective is we obtain the graph of piston velocity against the crank angle. Okay, so we have to, using those readings, we have to plot the graph. Now, piston velocity versus, listen, if you take on the x-axis, there is a crank angle. Okay, on x-axis, we plot, we put crank angle. On y-axis, we put piston velocity. Piston velocity. That's mean the OX, the cross scale reading. Then you divide the scale into every 10 degree, okay, until 360. Then here minus 5 or minus 10 and 5 and 10. Then you have to plot. You know the crank angle, so corresponding crank angle, you know what is the velocity also. That's what I did in the observation part. So then you have to plot all the points. Maybe coming this way or this one, I don't know. You have to plot all the points, then you have to row. I don't know how it's coming. That's what we are interested in. How the piston velocity profile is varying with crank angle. Okay? Then second, they ask, you have to plot on the same graph sheet, but another y-axis. What? That's a piston displacement. This reading also we got from the observation part. So on the same crank angle axis, let's say this one you take 0 or 10 or 20, then minus 10, then on the same crank angle, indicate all the corresponding displacement reading. Then you again draw. Okay? Again plot the graph, piston displacement versus crank angle. Okay? Then you familiar with the motion profile of the piston velocity versus crank angle. Okay? We are again and again telling we are interested in this profile. Okay? That's why we did this practical and come up with this graph.